let's talk philosophically about sorting. So we have many sorts out there that take n log n worst case time, right? Merge sort. You find its worst case input, it takes no more than n log n time. Now the question is, could we do even better than that? Find some sort whose Achilles heel takes only n log n time, or just n time perhaps. Is that possible? So to give us something concrete to hold on to, let's imagine that we have something I'll call the ultimate comparison sort. And comparison sort, I just mean it makes a sequence of calls to compare to decide how to order things. Let's say that TUCS, the ultimate comparison-based sort, is the algorithm that has the asymptotically fastest possible worst-case runtime. Okay, so you give TUCS an input, and no matter what, it will have just blazing fast, wonderful asymptotic runtime. And let's say that its runtime is R of n, which is its worst-case runtime in theta notation. So in other words, R of n is some function, and the worst-case runtime of TUCS is theta R of n. Okay, so what we can say then, this worst-case runtime of TUCS, it's some function, R of n, and I can tell you that that function, whatever it is n log n. Why is that? I'm gonna draw a little picture here. Okay, so this is TUCS. It is a worst-case runtime in theta notation, and I could say that that runtime is not going to be any worse than n log n. Why is that? So the reason there is that we already have an algorithm that takes theta n log n, merge sort, for example. Let's suppose TUCS, its worst case runtime was n squared, that is R of n equals theta n squared. That would be a proof that that's not actually TUCS, because we said by definition TUCS must be the fastest sorting algorithm asymptotically, and in that case it's not as good as merge sort. Okay, so we know, we have a proof of concept that there exists some algorithm which has n log n runtime. So this runtime R of n we can say is O of n log n. Okay, now again, just to kind of remind you, what is R of n? R of n is the runtime of TUCS in the worst case. So the runtime of TUCS is theta R of n, and here we're trying to speculate about that function R of n, and I could say that R of n is big O of n log n. So how about the worst case runtime of TUCS? How else can we bound it? Well, I can say that the worst case runtime of TUCS, R of n, is omega 1. And I'll put it here on this diagram. And that basically just says the problem doesn't get any easier with n. And the question is, can we make a stronger statement than omega 1? Okay. So imagine here, you're trying to consider all possible sorting algorithms out there. Is there a better bound on the runtime of TUCS? Okay, I'm going to say yes. I think linear is a good lower bound. And the basic argument there is that whatever the runtime of TUCS is in the worst case, it has to be at least linear time, because we have to at least look at every item here. So this algorithm, whatever it is, TUCS's worst case runtime is going to be omega n. Okay? And that's just another way of saying it has to at least look at every item. You can't be so clever that you don't have to look at every item, because let's say you try and come up with a sorting algorithm that only looks at the first half of the items or something. Well, that's still n, right? Let's say it only looks at the first square root of n items, right? So if you give it 1,000 items, it only if you look at 10,000 items, it has to only look at the first 100 or something. That wouldn't make any sense, because there's all this stuff you haven't looked at. So I hope it's clear that the runtime of TUCS has to be at least linear time. And so in terms of all of our formal symbols here, I can say that the worst case runtime of TUCS, which is theta R of n, that function R of n itself is omega n and big O of n log n. And if all these O's and omegas are getting a little confusing, you can maybe just imagine that we have greater than or equal to or less than or equal to symbols, and I hope that will help demystify it. So it turns out that it is possible to do even better than n. And that runtime is going to turn out to be n log n. So we're going to show that we can actually do better than saying it's at least linear, to say it's at least n log n. And what that lower bound means, what's so interesting about this, is that across the entire space of anything you might imagine, across all of humanity's cleverness and ambition to try and do better, among all of those ideas, none of them is any better than merge sort asymptotically in the worst case. Okay, that's what we're going to show. So there's no need to go searching for an even better sort, at least in terms of asymptotics. And so what we'll do in the next little video is we'll start detailing this proof with a glorious game known as Puppy Cat Dog.